Hey everyone, welcome to this episode of KuTube. Before we begin today, make sure you have the following materials out. Either a copy of today's notes, if you need to print it, you may do so, or if you don't have access to a printer, please make sure you have a piece of loose leaf or graph paper preferably, with today's date and today's title on top. In addition to your notes page, you will need a ruler and a pencil. A pen should be out just in case you want to make sure you're doing corrections, but it's not necessary. All right, let's get started. So the first thing we want to talk about is what does it mean to be a solution to an equation? We've done a lot of work with linear functions, and we talked specifically about what does it mean to be a solution. So really quickly on your piece of scrap paper on the top of your notes, just jot down what does it mean to be a solution to an equation. All right, if you need another moment, just pause the video. However, let's kind of really think about the representation that's being shown here. Being shown here, I'm giving you guys a linear function shown as a graph. And when we talk about solutions to any linear function, in this case, we have infinitely many solutions, right? We talk about how there are infinitely many points that show up on this line. Now, when we look at this as readers, though, we want to specifically choose point values that actually are nice integer values just for our own sake. But when we talk about solutions to an equation, we're looking at points, x and y, that'll satisfy that equation. There's two ways to think about this. Visually, it's points that show up on the line. Mathematically, it's the x and y value that satisfies the function rule or the equation. Utilizing this idea of a solution, today we're going to really move forward into understanding how to solve systems of linear equations. Before we begin, though, we do need to review a little bit about what we know about linear functions. So I'll ask you guys in a moment to pause the video and access the Jamboard that's located on Google Classroom and identify the three forms of the linear functions. So go ahead and pause the video, access the Jamboard, fill in the three forms on the post-its, drag the correct equation to the right spot, and then identify what's the benefit of each linear function form by typing in on each respective post-it. When you're ready, unpause the video and we'll continue with the notes. All right, so at this point, hopefully you have found the three forms of a linear function, identified the correct equation that matches the form, and identified the benefits. As we know, there are three major forms of a linear function. We should feel comfortable getting an equation in slope-intercept form, in standard form, and in point-slope form. Very similar to the names of it, each of the forms have benefits, right? We know that if we are given an equation in slope-intercept form, y equals mx plus b, we know we can pull out the slope easily and the y-intercept. If we are given something in standard form, we know that it's really easy to identify the x and the y-intercept. And finally, if we're given something in point-slope form, that's giving us a lot of information about the slope of the line as well as one coordinate point that shows up on that line. So we're going to be utilizing these two major features. We're utilizing what we know about solutions to an equation today, and we're taking everything from our last unit in terms of the different forms of a linear function, and we're applying it today's lesson on solving systems of equations. This is a pretty meaty lesson, so I do recommend at any point during this video, if you need to, pause the video, rewind it, or take a break. But let's kind of get started. Today we've got a lot of goals. We're going to first talk about what does it mean to solve a system of equations. Then we're going to head into using multiple methods. There are three major methods for solving a system of equations. The first one's graphing, the second one's substitution, and the third one's elimination. Your goal today is first and foremost to know what it means to solve a system. Second, to actually utilize each of the three methods. And third and finally, to identify when is each of these methods the most efficient. So let's get rolling. In your notes, let's actually talk about what does it mean to solve a system of equation. Well, a system of equations is basically a graph that contains more than one equation. All right, so if I have a coordinate plane, and I'm going to use some different colors, I can have multiple linear functions, and I'm going to use different colors for that. All right, I don't just have to have two, it could be three. All right, that could be a system of linear equations. I could have one linear equation. Oops, sorry, I erased that little arrow. And I could have a parabola. All right, so when we're looking for systems of equations, the goal is to figure out where the lines intersect. All right, and when we talk about solutions to a system, we're looking at that one point, and I'm going to go back to two linear functions here. Right? A solution to one linear function is any point that falls on the line, but a solution to a set of linear equations is just that one point of intersection. This point right here is the only x and y value that'll satisfy this line as well as this line. So when we look at what does it mean to solve a system of linear equation, it means to figure out where the lines intersect. It's the one point that satisfies all the equations in the system. There are three major methods for solving systems of linear equations, and we're going to go over them each today. The first method is graphing, which is a little bit more time consuming. However, it gives us a nice visual of what's happening in the graph. The second method is substitution. This is a nice, easy way of applying what we know about evaluating expressions in order to substitute for systems of equations. And the third and final method is elimination. All right, all three methods have its pros and cons, and that's going to be something that you're going to be looking out for today. When working with systems, remember that equations of lines may appear in a variety of forms. Sometimes you might get a nice slope-intercept form. Sometimes you might have standard form. Sometimes you might recognize vertical or horizontal lines. And other times we might need to manipulate an equation to put it into standard form or put it into slope-intercept form. So really feeling flexible today with being presented with multiple linear functions in different forms is going to be really useful. So let's talk about different types of solutions. Now, because we're coming off of our linear functions unit, all of the systems that we're dealing with today will only contain linear or straight lines. We will not be looking at quadratics, but please keep in mind that systems can contain quadratics, all right, or parabolas. In this case, though, we're going to look at three specific types of solutions to systems of equations. One scenario will look like this. We have two linear functions, and they're intersecting at one point. We call this one solution. In this example here, the only point that will satisfy both linear equations here is this point here, x comma y. When I plug in x and y into the equation for this line here that I just highlighted in purple, it will make that equation or function true. If I plug in that same xy value for this line that I'm highlighting in yellow, once again, it will make that equation or function true. It's the only solution that will make that equation or function true. In the second set, we're going to see that there is no solution. I'm actually going to keep writing this in red. I apologize. And we know that this system of equations has no solutions because we're really dealing with a set of parallel lines. And a set of parallel lines, we have no point of intersection. They both go on infinitely in both directions, which means that they will never intersect. Finally, we have a set of, what do we call these? Do you remember? Good, coinciding lines. What do you think about the solution set here? Good, this would have infinitely many solutions. Let's see if I can fit this. Many solutions. Sorry for my messy handwriting. And this has infinitely many solutions because no matter what point we choose on either line, it will satisfy either equation. Visually, we see that there are infinitely many ordered pairs or coordinate points that show up on both lines. Now that we know what it means to solve a system, and we know the different types of solutions, let's actually move on to identifying solutions for a linear function. So in these two examples here, and you also see them on your notes, you're going to notice that I've given you an ordered pair. We want to know whether the given coordinate is a solution to the given system. Now visually, we can take both of these equations, we can plug it into Desmos, and we can see that if this is the ordered pair, or this is the coordinate point in which both lines intersect. However, we want to do this mathematically. So the one way to check to see if a given coordinate is a solution, we actually want to take this x and y value and plug it into each of the equations and see if it satisfies it. So let's go ahead and do that. So I'm going to take -1, 2, and I'm going to plug it first into 2x plus 5y equals 8. And we want to see if that satisfies it. So I'm going to do some quick math here. I'm going to replace my x with -1, my y with 2. 2 times -1 is -2, plus 10 equals 8. And that is true. 8 equals 8. So I can safely say it definitely exists on this line, right? It's a solution to that first line, but I need to see is it a solution to the second line. So I'm going to take 3x minus 2y equals 5. I'm going to do the same thing. I'm going to plug in -1 for x. I'm going to plug in 2 for y. 3 times -1 is -3. Minus 2 times 2 is 4. Does that equal 5? Unfortunately, it does not. -7 does not equal 5. So we can say no. -1, 2 is not a solution. All right. Now what we do know is this ordered pair exists on this first line, but it does not exist on that second. Since it does not satisfy both equations, it's not a system. It's not the point of intersection. So go ahead, let's try example B out. We have 1, 3, and we're seeing whether or not that is a solution to both equations here. If you'd like to try this out, you can pause the video and unpause when you're done to check your solution. Otherwise, you can keep watching as I'm going to solve this out together as a class. All right, so I'm going to take 1, 3, and I'm going to plug it into my original equation. Let's try to keep this consistent. I'm going to do the first one in red. So I'm going to take 1, 3. I'm going to replace x with 1. I'm going to replace y with 3 into that first equation there. All right, we got 2 plus 3. Does that equal 5? Yep, 5 equals 5. So we know it exists on that first line. Off to a good start. Now I'm going to try the same thing with the second equation. We've got -2x plus y equals 1. I apologize for the red one. I should have started by writing it too, so I'm going to go back and add that in. All right, and we're going to plug in 1 for x, 3 for y. -2 plus 3, does that equal 1? It sure does. Since it satisfies both equations, this is a solution to the system. What this means here is that if I were to graph these two lines using Desmos, 1, 3 would be the point of intersection. That would be the point at which both lines intersect. Now that we know how to determine if an ordered pair is a solution to a system equation, let's start talking about how to actually solve it. So we did talk about 3 different methods. The first method is graphing. This one here is the most time consuming, but the benefits of graphing is it gives us a nice visual. Now, the first thing I want to talk about is some things that we might notice. You might notice the nice big curly braces. A lot of times when we deal with systems, you're going to see this giant curly braces. This is determining that there are multiple functions being shown here. Now keep in mind, since we're coming off our linear function, take a look at both of these equations given. Are they both linear functions? Yes. All right. And in Algebra 1, we really only deal with 2 functions. In Algebra 2, you might be looking at systems of 3 functions. In linear algebra, we look at as many functions as we want, right? We're just looking to see at what points do those lines intersect. So let's start with the first one of graphing. Now I take a look here and I'm going to first ask myself, what do I notice about both of these linear functions? Well, in this one that I'm going to highlight in green, I notice that this first one's in standard form. So I'm going to use what I know about standard form and I'm going to graph 3x plus y equals 9. I know that if I cover up x and solve for y, y is 9, which means that my y-intercept is at 9. 1, 2, 3, 4. So I'm going to count up to 9. If I do the same idea and cover up y now, right, replace y with 0 and solve for x, my x value is 3. In other words, my x-intercept is 3. Now I'm going to take my ruler, which I don't obviously have online, but if you guys can at home, and I'm going to connect these 2 lines as straight as I can, draw arrows at the end. All right, the next one we're going to do is we're going to graph y equals -x minus 1. Now I notice here that this one's in what form? Good, slope-intercept form. So I'm going to start by plugging in my y-intercept of -1, and I'm going to count up and over with a slope of -1. So I'm going to go down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1. And I purposely like to kind of do as many points as I can, just so I can make as accurate of a line as possible. So as I do that on my board, go ahead and do that on yours. And I'm gonna draw arrows at the end. And I did a little mess up here. All right. Actually, I'm gonna redo this one. Sorry, it's a little bit hard. Okay. All right, there you go, you had it. Using a ruler is a lot more accurate. All right, now that we have a visual, we can see that the first line in green is 3x plus y equals 9. If we want to be really fancy, notice I'm using two different colors. I can even go in and actually label this 3x plus y equals 9. This is totally optional. In the blue graph, I'm going to label as y equals negative x minus 1. And now we have to look for a solution. Well, the solution to these equation is the point of intersection. So I'm going to look here and I'm going to see, oh, this point's at 5, comma, negative 6. And that's my solution to this system of linear equations. Now, let's think about how we can quickly check. Well, visually, we can check that this is the point at which it intersects. However, mathematically, we can check by actually plugging this in. And what I like to do is use some mental math, right? I'm going to plug in 5 for x, I'm going to plug in negative 6 for y. In my head, I'm going to do 3 times 5 is 15, plus negative 6, that does gives me 9. Quickly, I'm going to check the second one. It needs to satisfy both equations. Negative 6 is equal to negative 5 minus 1, correct. Now that I know that it satisfies both equations, we in fact did graph this correctly. All right, so let's move on to example 2, same idea here. So once again, I'm giving you a system. I see that with the curly braces. All right, and I'm going to ask that you guys graph this independently. Go ahead and pause the video, and then when you're ready, unpause it, and we'll go over this together. All right, let's start going over this problem together. In example B, I'm going to take a look at this first equation here. We notice that this is in slope-intercept form. I'm going to do this and try to color coordinate this in red. My y-intercept is negative 1, and my slope is 1/2. So I'm going to go ahead and count up 1 over 2. Up 1 over 2, up 1 over 2, down 1 over 2. Now keep in mind, we don't need to plot this many points, but for me, I know that it's a little bit more difficult to do it on the computer, but here we go. All right, so I'm going to label this line as y equals 1/2 x minus 1. All right, the next line that we're going to do, I'm going to plot in blue. Once again, utilizing different colors if we're able to. If not, that's all right. I notice this is in standard form, so I'm going to start by looking for the intercepts. I always like to plug in x for 0 first, so I cover that up with my finger, and I say y is equal to 1. So my y-intercept is at 1. Then I'm going to cover up my y, and I'm going to solve for x, and my x-intercept's at negative 2. Okay. So now we've got 2 points. I'm going to kind of plot this line as best as I can. And we should notice something immediately. We notice that these are a set of parallel lines. All right, and if I were to really double check this, remember, we can really take this. We can look for the slope here. We know parallel lines have the exact same slope. So if we're nervous we plotted this wrong, we can always look back at other ways to check our work. If I were to put this in slope-intercept form, I do notice that that slope is in fact 1/2. So we know we plotted this correctly. I'm actually going to label this blue line 3x minus 6y equals negative 6. So what do we know about lines that are parallel? Well, we know that they'll never intersect. Since they'll never intersect, we're going to call this no solution. All right? So, how do we feel about graphing? Good. Let's move on to our second method. The second and third method is a little bit more complex, and it requires us to use a lot of previous knowledge. All right? The second method that we're really going to talk about is substitution. Now, in today's class, I'm really going to prompt you with specific methods to solve each problem, but just keep in the back of your mind that eventually you'll be given a system and it's going to be up to you to identify the most efficient method. So let's talk about a little bit about when do we want to use substitution. All right, so that's going to be our first goal. Well, let's take a look at these two systems that I'm highlighting in yellow here. Take a moment independently and identify anything in common about these two problems. What do you notice about each of these systems? Hopefully in both of these systems, you should have noticed that one of them's in standard form and one of them's in slope-intercept form. More specifically, when we have something in slope-intercept form, one of my variables are already isolated. So when we use substitution, we kind of notice that one of our variables is already solved for. Since y is equal to the expression x minus 1, I can substitute that into my first equation. Similarly, in the second one, I have y is equal to negative 3x plus 5, and in theory, I can substitute that into my second one. So if you ever notice that one of your equations is already substituted for a specific variable, right, manipulated in a form that we have a variable solved, we can always plug it into the second one. And that's really going to prompt us to use substitution. Let's now look at elimination. I'm going to change colors so it makes it a little fancier. What do we notice about both of these systems? Good, hopefully you've noticed that both of them are in standard form. More specifically, as we start to get better with elimination, you're going to notice that all my x's are lined up, all my y's are lined up, and all my constants are lined up. And specifically, I notice that these two y values are opposites. All right, now once again, constants, all my y values, and all my x values. Now in this case, I don't notice any of them that are opposites, and that's okay, and we'll talk a little bit about how we can create a better problem that lends itself to elimination. All right, so let's actually get into substitution elimination. If this slide confused you a little bit, take a deep breath. We're just going to actually go over each of the methods. These two are a little bit harder, but it gives us a nice way of solving it mathematically. Because graphing, as great as it is, it's very time consuming. All right, so in example A and B, we're going to solve by using substitution. Like we said before, in both of these examples, you're going to notice that one of the equations has a variable solved for. So in theory, what I'm going to do in example A is I'm going to take y equals 6x minus 11. And I'm going to say my value of y is equal to the expression 6x minus 11. So I'm going to take this and I'm going to substitute y into the second equation. And if you need to write that down, you can. Substitute y into the second equation. So every time I see y, I'm going to replace that y with 6x minus 11. So let's do that. We have 2x minus 3 times the quantity, well, that y is 6x minus 11, is equal to negative 7. I just took this 6x minus 11 and replaced it here for y. All right, so from here, we're just going to solve this out, and you're going to notice that we're going to solve for x. Negative 2x minus 18x plus 33 is equal to negative 7. I'm going to combine like terms. Negative 2x minus 18x gives me negative 20x plus 33 equals negative 7. I'm going to do some inverse operations in my head. I'm left with negative 20x is equal to negative 40. X is equal to positive 2. Now, unfortunately, we're not done. We now know that the x value of my solution is 2. I need to find y. Now, I can take this value of x and plug it into either linear functions, because remember, if we're looking for a system, a solution to a system, we're looking for the x and the y coordinate that satisfies either of the equations. So in theory, when I plug in x into either of these equations, right, I should get a y that works out. So for me personally, I'm going to plug it into the first one. Doesn't matter if you want to try it out and try the second one, you're totally welcome to. So y is equal to 6 times 2 minus 11. Y is equal to 1. So let's write our final solution. I'm actually going to circle this in red. I apologize. So my solution, the point at which these two lines intersect, is 2, 1. I'm going to circle, I'm going to box this, and for the sake of our notes, I am highlighting it too, so you can see this nice and clear. My solution is 2, 1. All right. So let's go ahead and try out example B. Once again, if you'd like to pause the video and try this on your own, you're welcome to. Otherwise, we can do this together. So in example B, I'm going to first look to see if there is an equation that lends itself for me to substitute. And we notice here that y is equal to x minus 1. So I'm going to take this value for y, and I'm going to plug it in here. So every time I see y, I'm replacing it with x minus 1, because y is equal to x minus 1. So I'm going to start with that first equation, 2x minus 3 times the quantity x minus 1 is equal to negative 1. Hopefully that color coordination is helping you. From here, we just use kind of what we know about solving equations. We are going to distribute that negative 3. Negative 3x plus 3 is equal to negative 1. We're going to combine like terms. We're going to solve for x. X equals positive 4. All right, once again, once we solve for x, we now need to take x and plug it into either one of those equations. So realistically, I personally think that plugging it into the second equation is a little easier, right? Y is equal to 4 minus 1. Once again, it doesn't matter. Choose which equation you think is more efficient. So now we have an x coordinate point and we have a y coordinate point. That means the point at which these two lines intersect is 4, 3. Now, can you identify two different ways in which we could check our solution? Good. The first way that we can check our solution is actually to plug 4, 3 into both of these equations. If 4 and 3, when plugged into my x and y value, satisfies it, we know that this is the point of intersection. The other way is to visually look at it, right? We can graph both of these equations by hand and see if 4, 3 is the point of intersection, or nice, quick, easy way is to use Desmos. Use that graphing calculator, plug in both of those equations, and see if the point of intersection is really 4, 3. All right, how do you feel about substitution? All right, awesome. Let's move on to elimination. Now, elimination's a little bit trickier. So let's take a look at these 3 examples here, okay? Now, you're going to notice that in elimination, I'm giving you 2 linear functions that are already in standard form. So our job here is to really determine which is the better value to eliminate. Our goal is to eliminate one of the values. Now, I'm just going to try my best to color coordinate this. We see that our x's are lined up. We see that our y's are lined up. And I'm actually going to ignore my constants for right now. Once again, in example B, I see my x's are lined up. We've got a coefficient of 1 and a coefficient of 2. And I see my y's are lined up, negative 1 and positive 1. These 2 examples here, I'm going to put 1 star on top. And I'd like you guys to do the same in your notes. The reason these are 1-star examples, nice and easy, is because I noticed that we have a set of x's in this first example that immediately will be eliminated. Notice that negative 4 and positive 4, if I were to add those together, eliminate. Those cancel out. In the second example, you're going to notice the same thing here. Negative y and positive y, right? Negative 1 and positive 1. Those coefficients cancel out. However, in example C, we're going to notice here that when we actually highlight our y's and we highlight our x's or pay attention to those, there is no opposite coefficient, which makes it a little bit trickier. All right, I personally love elimination because I think it feels like a little bit of a game. So let's actually start off with nice, easy examples, and then we'll move our way to example C. In example A, we notice that negative 4x minus 2y equals negative 12. 4x plus 8y equals negative 24. Like we said before, notice that those coefficients are opposite. Those are going to cancel out. So in my brain, I'm eliminating the terms with x. All right, I'm just writing that there just to give you an idea of what I'm doing. So I'm going to show that I work here. I'm going to take both of these equations. My goal is still the same, to see the point of intersection. And I'm going to put a giant equal sign. I'm going to treat this almost like a giant addition problem. All right? And I'm going to look up and down. I'm going to start from the top and go to the bottom. Notice here negative 4x plus 4x, that does cancel out. Now I have negative 2y plus 8y. That gives me 6y is equal to, what's negative 12 minus 24? Good, negative 36. From here, I'm going to solve for y. Y is equal to negative 6. Now that we know that y is equal to -6, just like we did in the past, I need to know my x value. I can substitute this y equals 6 into either of these original equations to see if it holds true. Not to see if it holds true, to find my x value. So in this case, it really doesn't matter which one you choose. I'm going to choose the second one just because I like to deal with positive coefficients, but really there's just no, it doesn't matter. So I'm solving for x, 4x plus 8. If y is -6, I'm going to solve for my x value, 4x minus 48 equals -24. I'm running out of room. 4x is equal to, was it -24? Positive 24, sorry. X is equal to 6. So here we have our solution. All right, I'm going to try to make myself room. My solution to this equation is 6, right? That's my x, and my y is -6. That's my solution. That's the point at which those two lines will intersect. All right, let's do example B. Once again, I see that both of those y's have an opposite coefficient. So in this case, I'm going to eliminate the terms with y. I personally always like to rewrite the problem, almost like a giant addition problem. I'm going to read up and down. So I'm going to start from the left. X plus 2x gives me 3x. I am going to put a giant addition sign here. -y plus y, that does in fact cancel out. Sorry about that. So we have 3x, this cancels out, is equal to 30, which means x equals 10. Now that we know our x value, we can plug it into either of these equations. I personally don't have a preference here. I'm going to use 2x, the second equation, plus y is equal to 19. I'm going to plug in 10 for x, and let's solve for y. So we get 20 plus y is equal to 19. I subtract 20 on both sides. Y equals -1. Now we have an x value, we have a y value, and our solution here for this problem is 10, -1. I'm going to box that solution for the sake of this video. I'm going to highlight it. And once again, two ways to check that, right? We can plug that into Desmos and see if that's actually the point of intersection. We can take the time really nicely right here. This is a nice easy one to plug in. When x is 10 and y is -1, it does in fact satisfy both of those equations. Take that time, plug it in. All right, our last and final example is a little bit tricky. So if you need to take a break, pause the video. If otherwise, take a nice big deep breath, because this is the one that I love and requires you to think a little bit. So in this example here, I notice that my 5x and my 10x has a coefficient of 5 and 10. Now, those don't easily cancel out. However, I'm going to think to myself, what are some options I can do? Well, let's say I decided to make this -10. And the way to make that -10 is, what would I have to do? Correct. Multiply everything by -2. Because keep in mind, I can't just multiply that first term. If I decide to make that first term -10x, I would need to multiply everything in that first equation by -2. All right? Now that would be a nice way of getting my x's eliminated. Oops, sorry. Oh my goodness. However, if I take a look at the next one and I say, all right, let's say I wanted to eliminate my y's. Well, I have +1 as the first coefficient and -7 as my second coefficient. So can you think to yourself, how can I eliminate the y's? Good. Hopefully you're thinking, I wish this one had a +7. So in that case, I would have to multiply every term in that first equation by 7. Now, I don't know about you, but I don't want to have to worry about multiplying every term by a negative. We are able to do that, but there's a lot more room for error. So we're going to go with that second option. We're going to multiply every term in that first equation by 7 to get a second term of +7y. So let's actually show how we're going to show our work here. Actually, I'm going to give myself a little bit more room. We have 5x plus y is equal to 9. We have 10x minus 7y is equal to -18. Giant equal sign. Now, once again, our goal is to get that second term right here, right? become positive 7. And to do that, I'm going to multiply every term here by 7. So I'm going to show my work here. My first new equation is 35x plus 7y is equal to 9. The second equation is 10x minus 7y is equal to negative 18. Now I can actually take a look at this from top to bottom, and we can actually solve this out. I'm going to first look here to the left, 35x plus 10x, that gives me 45x. The positive 7y minus 7y, that does in fact cancel out. 9 plus, little mistake here. Don't forget to multiply every term, shame on me. 7 times 9 is 63. All right, we're going to look at that last column here, 63 minus 18, which gives me 45. So x is equal to 1, getting a little closer. Now, once again, we just choose one of the equations from my original problem to actually solve for y now. I'm going to use that first equation, 5x plus y is equal to 9. I'm going to plug in x for 1. So 5 times 1 plus y is equal to 9. 5 plus y is equal to 4. So my solution here is 1, 4. I'm going to box that answer. For the sake of the video, I'm also going to highlight it. This means that if we were to graph 5x plus y equals 9 and 10x minus 7y equals negative 18, the point of intersection would be 1, 4. All right, elimination's a little bit trickier, but I would like you guys to try them out. So at this point right now, we've done a lot of work. We talked about how to graph. We talked about how to solve by substitution. We've also talked about how to solve by elimination. If you feel like you are very confident and ready to move on, you're going to move on to the HyperDoc. You can partner up or work independently to try out practice problems in the HyperDoc. You will need a colored pen for corrections. You will also need a piece of scrap paper. You're going to try problems from each section of the HyperDoc and then check your answers with the key that's shown. If you feel like I understood it, but you want a little bit more instruction, you're going to access the mini lesson video that's also located on Google Classroom. You're going to work together with me through a series of extra practice problems. We'll talk strategies and discuss ways to check your work. Otherwise, get started on one of our classwork activities. When you are done, you can move on to the homework. You have a two-sided homework. The front side is very skills-based. It is directly aligned to what we've learned in class. And then the back side of your homework is a little bit more critical thinking. All right, thanks for watching today's episode of KuTube. I hope this was helpful. I know it was a lot of information, but we'll get into talking a little bit more about strategy. But as of right now, I hope that you feel confident and feel good about how to solve systems of equations using graphing, substitution, and elimination. Thanks for